Today we discuss the rest of section 4.1. We start discussing theorem 2, the first derivative theorem for local extreme values. If f has a local maximum or minimum at an interior point C of its domain, and if f dash is defined at C, that means f is a differentiable function and it attains the extreme value, either maximum or minimum at C, then the derivative at that point is always 0. Okay, that is f dash C is equal to 0. Whenever a differentiable function attains its extrema, one of the extrema at C, we can say that the derivative at C is 0. Okay, this is because we know that what is f dash C? F dash C is equal to limit x tends to C f of x minus f of C divided by x minus C. This is the definition of the derivative of f at the point x equal to C. Okay, when you consider this example, this is our f y equal to f of x. Suppose this f attains its maxima at x equal to C. Okay, without a loss of generality, or you can assume f attains its minimum at x equal to C. Okay, on the either way. If f attains its maximum, then we need to evaluate this limit at the point C. Okay, so in order to evaluate this limit, we need to evaluate two different limits. Limit x tends to C minus f of x minus f of C divided by x minus C, and that should be equal to limit x tends to C plus f of x minus f of C divided by x minus C. So this is the left hand limit and this is the right hand limit. Both should be equal in order to get f dash C. Okay, so we need to evaluate these quantities. Whenever you consider left hand limit, we need to take x from the left hand side of this this x equal to C. So when you take x here, we can say that what is the value of f at x. Okay, so we can say that this, if you project, suppose this is our y-axis, we can say that this is the value of f of x and this is the value, this is our f of C and this is our f of x. Now we can say that f of x minus f of C is always negative because f of C is greater than or equal to f of x. So this f of x minus f of C is negative, and this x minus C is always negative. Okay, so this is the quotient of two negative quantity, so this is always greater than or equal to 0. This quantity is always greater than or equal to 0. Therefore the limit is also greater than or equal to 0. So we can say that f dash, from this we can say that f dash C is always greater than or equal to 0. From this, when you observe these two quantities, f of x minus f of C divided by x minus C, whenever we take x from the right hand side of C, when we take x from the right hand side of C, we have this is our f of x. Okay, here we can say that the same inequality holds for f of x and f of C. Okay, here f of C is greater than or equal to f of x. Okay, so the numerator is always negative quantity and the denominator is always positive because x is greater than or equal to C here. Okay, for nearby C, this x should be greater than or equal to C. So the numerator is negative and denominator is positive. So we can say that this quantity is always less than or equal to 0. Then when we take the limit, we can say that that limit is also less than or equal to 0. Then that is the limit is nothing but f dash C. So that f dash C is again, from the second case, we can say that f dash C is less than or equal to 0. From these two inequalities, we can say that f dash C should be 0. So whenever a differentiable function attains its one of the extrema at the point x equal to C, we can say that the derivative of that f at the point x equal to C should be 0. So this is the theorem, what we call the first derivative theorem for local extrema values. This is also called a necessary condition for attaining the local extrema or local maximum or local minimum of a differentiable function. That is very important. You should remember that this holds only for differentiable function. Okay. Now we have a definition here. Critical point. Okay, critical point of a function, an interior point of the domain of a function f where f dash is 0 or undefined is a critical point of f. Okay, if we consider an interior point, okay, suppose we have an interval like this a and b, then consider an interior point c. Okay, an interior point of the domain of a function, okay, where f dash is 0, or if in this point either you can evaluate f dash c if f is differentiable. Okay, if this is 0 or f dash not defined at the point x equal to c. Okay, in either case we can say that this c is the critical point. Okay, so any critical point, any interior point which has this one of these properties, either f dash equal to 0 or f dash is not defined, at x equal to c, then you can say that c is the critical point. Okay, so whenever you can as soon as you understand this theorem, you can say that at the extreme values this f dash is 0 if f dash exists. Okay, so we can classify all those points C such that either C should be an extreme point, the point of extrema, or at the point C derivative does not exist for f. Okay, the points with these properties are called critical points. Now we can understand how to find the absolute extrema of a continuous function f on a finite closed interval. Okay, a finite closed interval means simply we can write it as interval AB. Okay, when you given any continuous function defined on a closed interval AB, then what is the procedure for finding the absolute extrema of that function? Okay, you need to follow two steps. First, evaluate all critical points and endpoints of the interval. Okay, those are the possible points at which this f attains its extrema. Okay, and take the largest and smallest value among these. Right? For example, we can consider f of x equal to x square. Obviously, this is a continuous function defined on x belongs to -2, 1. Okay, suppose this is our interval -2, 1. We need to follow these two steps. First, we have to find all critical points. Okay, since this is a differentiable function, then critical points are obtained by equating f dash c is equal to 0. Whenever f dash c is equal to 0, we can write what is f dash x. F dash x is equal to 2x. Okay, then what is f dash c? F dash c will be f dash c is equal to 2 times c equal to 0. So this would imply that f dash c equal to 0. Whenever f dash c equal to 0 implies c equal to 0. Okay, so if suppose our interval is -2, 1, we can say that this is our one critical point. Okay, so the first step is to evaluate all critical points and endpoints. There. Now write critical points and endpoints. This is the first step. Critical points and endpoints are, the possible points are c is equal to -2, this is an endpoint, 0, this is a critical point, and 1, this is also an endpoint. Okay, and evaluate f of c at all of these points. Okay, when c is equal to minus 2, you can get f of c is equal to 4, and c equal to 0, we can get f of c equal to 0, and c is equal to 1, then f of c is 1, because f of c is c square. Clear? So from this you can say that this value 4 is the absolute maximum value and 1 is the absolute minimum value. So we can write the absolute maximum of f is 4 and absolute minimum of f is 1. Okay, this 4 attains at x equal to minus 2 and attains maximum of f is minus 1 at x equal to 1. Okay, so this is the conclusion. So in order to evaluate the maximum, absolute maximum or absolute minimum, you need to evaluate all critical points and endpoints. Okay, f attained is the maximum or minima at one of these points or some of these points. Okay, need not be one. Absolute maxima can be attained at more than one points, but the value will be, say, absolute maximum will be unique, but that can be attained more than one points. Next we can discuss another problem. This is another example in the textbook. Find the absolute maximum and minimum values of f of x at f of x equal to x raised to 2 by 3 on the interval minus 2 comma 3. So we need to follow the two steps that we have discussed earlier. So the first step is to evaluate all the critical points and endpoints. Okay, obviously the endpoints are minus 2 and 3. Now we have to evaluate the critical points. The critical points are the points at which f dash is 0 and or f is not defined, f dash is not defined. Okay, so first we have to evaluate f dash of x. Okay, f dash of x will be the derivative of x raised to 2 by 3, that is 2 by 3 times x to the power 2 on 3. Okay, on 3 minus 1. This is the derivative of x raised to 2 by 3. That is equal to 2 on 3 x to the power, what is 2 on 3 minus 1. Okay, that is minus 1 on 3. Yeah. So this is equal to 2 divided by 3 times x power 1 on 3. Okay, this is the f dash x. We know that this derivative never be 0. This never be 0. In order to get this is equal to 0, that 2 must be 0. Okay, so that is not possible. So this derivative is non-zero always. Clear? At x not equal to 0. When x equal to 0, we can say that this f dash x is not defined, because whenever x equal to 0, this denominator will be 0. So the function is the derivative is not defined. Therefore, the critical points is the critical point. Critical point is x equal to 0. So now we have critical points and endpoints. Those are minus 2, 0 and 3. So the values of z are if c represents a critical point and endpoints, then c must be minus 2, 0 or 3. Then corresponding f of c. Whenever x equal to minus 2, then that will be minus 2 power 2 on 3. And if x equal to 0, then this will be 0. And x equal to 3, we can get this is 3 power 2 on 3. Clear? So these are the values. We know that this value is always, this is, what is this value? This is equal to, we can write it as minus 2 whole square to the power 1 by 3, and this is 0, and this is 9 raised to 1 by 3. These are the values. Whenever minus 2 whole square is 4, so 4 raised to 1 by 3. So this will be 4 raised to 1 by 3, 0, 9 raised to 1 by 3. Okay, so the largest among these values is 9 raised to 1 by 3, and the smallest is 0. Okay, so we can say that we need, the second step is evaluate the largest and smallest one. Okay, so the absolute maximum is 9 to the power 1 by 3. It attains at x equal to 3, and absolute minimum is 4 raised to 1 by 3. Sorry, that is 0. Absolute minimum is 0 at x equal to 0. Okay, so these are the absolute maximum and absolute minimum. So this completes section 4.1. In section 4.1, there are two more examples, worked out examples. So you must try to do it as a homework, and if there is any doubt regarding those problems, please let me know the doubts, and we will arrange a Google Meet in order to discuss those doubts. Otherwise, we can conclude section 4.1. The next video onward, we will discuss the next sessions of this module.